Hello friends, welcome back to Secret of Electronics. In this video, we will learn how to interface a 4-digit 7-segment display with the 8051 or AT89S52 microcontroller using embedded C. This circuit diagram demonstrates how to interface a 4-digit 7-segment display with the AT89S52 microcontroller to display numbers just like a digital counter or clock. Let's break it down, starting with the microcontroller section. Here the AT89S52 is the brain of the project. It runs on a stable 11 MHz crystal oscillator with two 220 picofarad capacitors, which provides the clock signal needed for accurate timing. The reset circuit, made up of a 10 kilo ohm resistor, 0.1 microfarad capacitor, and a push button, ensures that the microcontroller starts cleanly every time power is applied. Of course, the entire circuit runs on a plus 5V supply connected to the VCC and GND pins. Now moving on the display section, this is where the magic happens. We are using a 4-digit 7-segment display which allows us to show 4 numbers at once like 1, 2, 3, 4. The segment pins A to G are all connected to port 3, P3.0 to P3.6 of the microcontroller through 220 ohm resistors R2 to R8. These resistors protect the display LEDs from too much current. Each digit common cathode D1, D2, D3, D4 is controlled by BC547 NPN transistors Q1 to Q4. These transistors act like electronic switches. When the microcontroller sends a signal from port to P2.0, P2.3, it turns on the corresponding transistor, which in turn lights up that specific digit. The 4.7 kilo ohm resistors R9 to R12 limit the base current to each transistor. Here's the interesting part. Even though we have 4 digits, the microcontroller only drives one digit at a time. It lights up each digit very quickly, one after another, faster than our eyes can detect. This technique is called multiplexing, and it makes the display appear as if all 4 digits are glowing simultaneously, saving a lot of pins and power. So in short, port 3 controls which segments light up, what number to display. Port 2 decides which digit to turn on, and by repeatedly switching between digits, we get a smooth 4-digit display output. Includes the standard 8051 register header, gives friendly names to ports, seg for segments, dis for digit intervals. These are the bit patterns for digits 0 to 9 for a common cathode display. Bit mapping assumes A to G DP on P3.0 to P3.7, DP not used here. Example 0x3f equal 0b 00 6 times 1 lights A B C D E F to display 0. If you ever switch to common anode, you would invert these bytes or write a second table. Delay underscore ms gives a simple timing. Display underscore number handles the multiplexing of all 4 digits. Main loop runs forever, counts down from 9999 to 1. For each count value, it calls display underscore number count 100 times to keep the display refreshed at a steady brightness while the number stays the same. Rough timing field 1 display underscore number lights 4 digits. multiplexing a 4-digit number. What happens here? The number is split into 4 digits, thousands to ones. All digits of this equal 0x00 to prevent ghosting. For each digit, enable the target digit line on port 2, 0x01, 0x02, 0x04, 0x08 with your BC547 low side drivers. Driving the P2 pin high turns the transistor on. Sinking current. The selected common cathode goes low. That digit lights. Output the segment pattern on port 3. Seg code DX. Hold 2 milliseconds so our eyes can see it. Turn the light off before moving to the next to avoid ghosting. A nested immediate loop that burns CPU cycles on a standard 8051 12 clocks per machine cycle with 11 MHz crystal. This approximates milliseconds. Now we need to generate the hexa file for our embedded C code. To do this, we will use Kill Vision software. So open the Kill Vision software on your computer. Once it's open, go to the project menu and click on New Vision project. I am naming this project 4_digit. After typing the name, click OK. Next we need to select our microcontroller type. In the search field, type AT89S52. You will see AT89S52 listed under microchip. Select it and click OK. After that, Kill will ask to add the startup file. Click yes, and when it asks again, click yes one more time. Now move your mouse cursor over target 1 in the project window and right click on it. From the menu that appears, click on Options for target 1. A new window will open. Go to the Output tab and here, check the box labeled Create Hexa file. After selecting it, click OK to save the settings. Next, click on the plus icon beside the target 1 folder. You will now see source group 1 inside it. Right click on source group 1 and select add new item to group source group 1. From the list that appears, select C file and give it a name. I am naming it 4_digit.c, the same as our project name. After typing the name, click add. Now open the C file that you just created. Copy the embedded C code. You can download it from the link provided in the description and paste it into this file. Once pasted, make sure to save your file. After saving, click on the Translate button. You will notice that the output window shows 0 errors, 0 warnings, which means our code compiled successfully. Finally, click on the Build button. After building, you will see that our hexa file has been successfully generated and saved inside the Objects folder of our project directory. Now open the project folder where your Kill Vision project is saved. Inside that folder, you will find a subfolder named Objects. Open it and you will see the hexa file that we just created. Next, we will use AVR and an Arduino Nano board as an ISP programmer to upload this hexa file into our AT89S52 microcontroller. Simply connect the ISP pins of the AT89S52 microcontroller to the corresponding ISP pins of the Arduino Nano board. I have already uploaded the Arduino ISP code to my Arduino Nano board, so it is ready to act as the programmer. If you would like to learn how to program the AT89S52 microcontroller using AVR and Arduino Nano in details, you can watch our complete step-by-step tutorial by clicking the I button on the top right corner of this video. Now open the AVR folder and move or copy your hexa file into it. I am renaming the file to main.hexa. This makes it easier to type the file name in the command later. Next, connect your Arduino Nano to your PC or laptop using a USB cable. Once connected, open the command prompt. Now we will start by running the first command. Do not forget to replace the COM port in the command with the actual port number where your Arduino Nano is connected. You can download all the required commands from the link given in the description below. After running the first command successfully, run the second command. Again, make sure to replace the hexa file name in the command with your actual file name, in this case main.hexa. Once you hit enter, you will see that the hexa file starts uploading into the AT89S52 microcontroller. When the upload process is complete, disconnect the Arduino Nano from your PC and also unplug it from the microcontroller. Finally, connect all the components together according to the main circuit diagram that we discussed at the beginning of this tutorial. And that's it. Your project is now ready to run. Now connect the circuit to a 5V DC power supply. After connecting, you will see the countdown running on the 4-digit 7-segment display. Do not forget to subscribe to our YouTube channel to watch more upcoming and interesting tutorials. And if you have any project ideas that you would like me to make and share as a tutorial, just let me know in the comments section. I will be happy to create it and upload a complete step-by-step video for you.